Hello folks, welcome back to Merrill Math. I'm Mr. Merrill, and today we're going to be talking about Lagrange Interpolation. This is a pretty complicated, I guess overly complicated method for turning 3 points into a quadratic function. Now, there are different ways to solve the problem that this method solves, kind of like most areas of math where you have a lot of different ways to solve a problem. But this is one way that actually works in a pretty interesting way. So let's take a look at sort of how this fits together. Now, when I talk about quadratic functions, I'm talking about something in the form y equals ax squared plus bx plus c. So we've seen those. We know them, we love them. So for our, I'm only going to do one example because these are somewhat time consuming. We'll see how long this video ends up being. So, and we're going to solve this problem in another way in a different video where we talk about some other methods for doing this. There's also, you can approach these in a system of equations as well. And for a lot of students that makes a little bit more sense, but the Lagrange interpolation works in a really interesting way. Some might even call it elegant. Most of you would probably call it frustrating. So we're going to take a look at this. We want to find a quadratic function that contains these 3 points. Now, when we're solving a problem like this, one thing we have to be careful about is the 3 points can't be like vertical from each other, so you can't have a point, 2 points with the same x coordinate. So one quick way, if you're working on a quiz or a test, because sometimes math teachers, we like to throw curveballs at students just to make sure they're paying attention. So in the case of these, we want to make sure that all of the x values are different first, because that's one way that we can just quickly look at the problem and say whether or not it's solvable. So in this case, this problem is solvable, so we are going to tackle this one. And as we're looking through this, there are sort of 3 different parts that we have to attack in order to put those together and find the solution. I just realized I'm doing a bunch of hand gestures that you can't see on camera, but that's okay, they don't really help. Anyways, so the way that Lagrange interpolation works is, what it does is it takes 3 polynomials with specific solutions, and it sort of smashes them all together, and it creates a quadratic function. So the way that we make that work is we sort of take, now if you'll remember, the 3 points that we had, 1, -2, -2, comma 1, and 3, comma 6, we're going to kind of break these apart in 3 different ways. So for the first point, we have 1, -2. The other 2 points we're just going to zero out. So the y values are going to be 0, and we're going to use that to sort of create a polynomial and do a little bit of work with it. So what do I mean? Well, what we're going to do is I'm going to take my y value, and I'm going to say -2 is equal to some constant, let's call it j, times these 2 pieces. So we'll say, now we need to turn them into factors. So if we have, this is a solution to a polynomial, we need to say what factor gave us that solution. Let's take a sidebar real quick. So what do I mean by that? So if I have something like x, make sure I'm not bleeding through on this other page, x plus 4 and x minus 1, and that's equal to 0, right? So if I have something like this, the zero product property, or the ZPP, tells us that x plus 4 is equal to 0, or x minus 1 is equal to 0, and this is basic like solving quadratic functions. So when you're finding the zeros or the roots or the solutions of a quadratic function, there's a lot of steps up here. Maybe you got this to this point by factoring. But if you want to find the solutions of this, you say, okay, x plus 4 is 0, x minus 1 is 0. So that means that x is equal to -4, or x is equal to 1. So in this case, that's what that would look like. Now, with this method, with Lagrange, we have to kind of go backwards. So if we start with an x value, we have to go backwards and say, what did our factor look like in order to get there? So that's what we're doing for this problem. So back to this. So if my 0 is, if y is 0 at -2, that means my factor looked like this, x plus 2. Because if x plus 2 is equal to 0, then that means that x has to be -2. This is, for a lot of students, like a huge hurdle to get over. A quick way to just kind of power through these types of things is just to say, you just do the opposite inside the factor. This is a +2, that was a -2. This is a +3, that means in here it's going to be a -3. But it's important to not lose sight of what it is you're actually doing. So at any rate, that's what that's all about. So you might be asking, what about this guy? I used the -2, so what happens to the 1? The 1 actually gets substituted in for these x's. So we're going to say -2 is equal to j. We're going to solve for this here in a moment. 1 plus 2 and 1 minus 3. And then I get some values here, and then I have to figure out what j is. So in this case, I get 3. 1 minus 3 is -2. This ends up being -6. So -2 is equal to -6j. And in this case, now some teachers will use different variables here. Don't feel like you're married to j. I'm going to use j, k, and l just because they're kind of in the middle of the alphabet. I don't want to use a, b, and c because I used a, b, and c back here, and these values that we're finding for j, k, and l aren't going to just plug into here. That would be nice, but that's not how that works. So we had to pick some different variables. Some teachers, when they approach this, they'll use like a capital A, capital B, capital C for these 3 parts that we're looking at. Different teachers do things differently. So in any case, we have this. We can solve for j. -2 divided by a -6, that's going to be a positive. We'll reduce the fraction 1/3, and that's equal to j. Now, what happens here is this is our first polynomial that we're going to combine with the other 2 that we're going to find. So it's going to be 1/3 times this times that plus some other number times some other factor times some other factor, and so on and so on. And then what we end up with is a really gigantic, horrible looking polynomial that then will simplify down into something a bit more manageable. So that's the first part. The second part kind of follows almost exactly the same, except now this is a 0 and this is a 0, and then we've got these values that we're using. So my y value is 1, so I have 1 equals, I've got k times this factor. I'm going to say x minus 1, and then this factor, x minus 3, and then I have to substitute -2 in for x and then solve. So 1 is equal to k times -2 minus 1, -2 minus 3, and then I get some numbers here. So -2 minus 1, that's -3, -2 minus 3, that's -5, this times that, that gives me, what is that, 15? So I've got 15k is equal to 1, so we know that k is equal to 1/15. Sometimes when we're doing this method, we end up getting a lot of weird fractions, and a lot of times those fractions will reduce down and simplify with other things and you get nice neat numbers. Sometimes that doesn't happen. So we kind of have to be on our toes and have all of our fraction skills up to date. So don't feel like just because you left elementary school that you don't ever have to work with fractions again. So the third part, we're just kind of working down the line here. So the last two numbers are going to be the points that we were originally looking for. Notice that we had 2, 1, there's negative 2, 1, 3, 6, we've got 3, 6, the other ones are zeroed out. So for this one, we're going to say 6 is equal to L times this factor, x minus 1, and then this factor, x plus 2, and then we have to substitute 3 in for this x, so 6. I've got 3 minus 1 and 3 plus 2. So here I've got 6 is equal to 3 minus 1 is 2, 3 plus 2 is 5, 5 times 2 is 10, so I've got 10L, and then I just have to divide this to solve for L. So L is going to be 6/10, which reduces to 3/5. Now, how do we use all of this? So we've found a bunch of information about these polynomials that we're going to be using. So there's this guy, and there's this guy, and then there's this guy. So those values that we found, we're going to substitute in for J, K, and L. So how does that look? Well, when we start going through that, like I said, this is kind of a long process. It takes a little bit of time, but once you get used to it, you'll be able to do it. Most math teachers, if they're not completely sadistic, won't make you do this a ton. So like if you're taking a quiz or in a test situation, they won't make you do a lot of these, but some math teachers will be like, you should be able to do like 1 or 2 Lagrange problems for a test or a quiz, because they take kind of a long time. So for this, using the information that we had here, we're going to say, let me see if I can write this here. We've got 1/3 times our factors. What did we have? X plus 2 and x minus 3 plus 1/15 times those two factors, x minus 1 and x minus 3. And then for the last one we had 3/5 times those two factors, x minus 1. When you're doing these types of problems, you will very frequently run out of space, so plan accordingly. X plus 2. I didn't really plan accordingly. So this is the polynomial that we get. So what we're going to say is something like y equals this. Now, if we just left it like that, that technically would be correct, because this is a polynomial. This is a quadratic, kind of, that gives us those points on it. Those are points that are on this, because we specifically created it to be that way. Most teachers will want you to reduce it, and this does hopefully kind of condense down into something that's a little more manageable. So in this case, we have to do a little bit of FOIL stuff here, and then we're going to have to combine some like terms and things like that. So let's see here, what do we get? So we're going to say y equals 1/3. If we FOIL these two guys, I'm going to get x squared minus x, so I do the sum here and then the product of those two, so I've got negative 3 times 2, that's going to be a negative 6, and then 1/15 x squared, sum of those, that's minus 4, and then the product of those, that's a plus 3, and then 3/5, and then I've got x squared plus x minus 2, and then we have to do some distributing of these fractions inside of there. Now, a lot of this work is going to be just kind of, I don't want to say busy work, but it kind of is. If you have a calculator with a computer algebra system, like an Inspire CX CAS, I'm trying to see if I have one within arm's reach. I don't. I mean, it's over there, but it's beyond arm's reach. If you have like an Inspire CX CAS, like the old one or the new one, anything with a CAS, so TI-92, TI-89, I'm sure there's Casio calculators that have CAS systems, but who uses Casio? So you can use a calculator with a CAS system to do this. CAS, if you don't know, it stands for Computer Algebra System. So I think it stands for that. I'll probably edit this out. Okay, so once we have something like this, we can do our distributive property, and we can kind of crank this down. You'll have to do some fraction things, finding common denominators and all that fun stuff. But once you crank this out, what you end up with, because I'm a math teacher type guy, so I'm going to skip some steps here. You end up with something like this. Y equals x squared plus 0x minus 3. Or we could just say y equals x squared minus 3. Now, if we go back to our original points, we had 1, negative 2, negative 2, 1, and 3, 6. So these were the original points that we were working with. Now we can test this x squared minus 3 and just make sure that that works. These are your x values, these are your y values. So if we square 1, we get 1, and we subtract 3, we get negative 2. That works. Square 2, square negative 2, you get 4, subtract 3, you get 1. That works. 3 squared is 9. 9 minus 3 is 6. That also works. So we end up with a very simple solution from a slightly complicated or convoluted process. So Lagrange interpolation isn't something that you're going to use a ton. It's a very interesting, and it's a powerful method, but it's a bit more work than it's worth. There are some other methods that we can apply to problems like these. We might talk about a system of equations method next to deal with a problem like this. So that is it for today. Thanks for watching.